This mini-lecture introduces another periodic trend, electronegativity, and we'll see how it can be used to determine the best Lewis structure for molecules that exhibit resonance, meaning they have more than one Lewis structure. We'll also see some Lewis structures with exceptions to the octet rule. Sometimes a molecule or polyatomic ion has more than one possible Lewis structure, such as the carbonate ion CO3 2-. Since carbon needs to share more electrons than oxygen to achieve a full octet, it will act as the central atom, and since carbonate is an ion, the entire structure is enclosed by square brackets with the overall charge indicated on the outside. Adding up valence electrons, carbon has 4 and each oxygen has 6, for a total of 22 valence electrons. But wait, we also have the -2 charge on the ion, which adds another 2 electrons for a final total of 24 valence electrons. Then we place bonding pairs in the structure wherever a bond is implied, so between each carbon and oxygen pair. This accounts for 6 total valence electrons, which we subtract from our total of 24, leaving 18 valence electrons that need to be placed onto the structure as lone pairs. We start by adding to the terminal atoms. Each oxygen currently has just 2 electrons, so they each need another 6 electrons to satisfy the octet rule. So we add 3 lone pairs to each oxygen. This uses up our remaining 18 valence electrons, so we can't add any more dots to the structure. But this leaves carbon without a complete octet. So since we can't add any more dots, the only option is to change a lone pair on an oxygen into an additional bonding pair, creating a double bond between the 2 atoms. Now, our final structure is complete as all valence electrons are accounted for and each atom satisfies the octet rule. But how do we know which of the oxygens donates the lone pair? Here we used a lone pair on the upper right oxygen, but what if we instead moved a lone pair on the lower right oxygen to form a double bond? This new structure is just as valid as the first and represents a different structure as a different oxygen atom now has a double bond. And there is yet one more option, because we also could have moved the lone pair from the left oxygen to create a double bond. This new structure is also just as valid as the first and represents yet another different structure since a different oxygen atom now has the double bond. So which of these structures is the correct structure? The answer is none of them and all of them. In nature, molecules that display resonance have the ability to share electrons across multiple bonds so that the 2 electrons needed to satisfy the octet rule on oxygen actually spend their time spread over all 3 of the bonds in the structure, and we say that the electrons are delocalized across the structure. However, we can't easily represent this with a Lewis structure, so the best we can do is show all 3 resonance structures to give the complete picture. We use double-sided arrows to indicate that the 3 individual structures are resonance structures of the same molecule, and this means that none of these 3 individual structures actually exist, but the molecule instead will exist as a hybrid of all 3 structures. Since single bonds are longer than double bonds, we see proof of the hybrid structure if we measure the bond lengths in the molecule. If one of the bonds is shorter than the other 2, this indicates that the double bond is located at one of the 3 positions. However, in the case of the carbonate ion and the similar case of the nitrate ion shown below, the bond length for all 3 bonds is in between the expected length of a single and double bond, indicating that all 3 bonds are the same length and none of them are single or double bonds. So this proves that the double bond is delocalized across all 3 bonds, creating basically a 1 1/3 bond for each bond. Now, one analogy that's often used for resonance structures considers crossbreeding. If a German Shepherd and a white lab represent individual resonance structures in this analogy, then we consider the hybrid puppy that is created from these 2 parents. The puppy has features of both the parents, but it would never be recognized as a German Shepherd or a white lab individually. Instead, it would most likely prompt questions from others about its parentage, as I'm sure most owners of hybrid breeds or adopted mutts of unknown origin can confirm. So, just like the hybrid puppy, a molecule with resonance structures has attributes of all the resonance structures that combine to create the true structure, which means an individual resonance structure on its own could never be used to represent the hybrid, as they look entirely different. Lewis structures are drawn so that electrons are localized to one atom's lone pair or between atoms as a bonding pair. Yet in reality, electrons are more mobile and can be delocalized across a structure and do not need to stay on one atom or between two atoms at all times. Occasionally, you may see resonance hybrid structures drawn with dashed lines to indicate partially delocalized bonds, as we see in the ozone structure shown here. But when faced with a problem that asks you to draw a Lewis structure for a molecule that displays resonance, a complete answer for such a problem should include all valid resonance structures. Electronegativity is a property that represents the relative ability of an atom to attract electrons towards itself when sharing electrons in a bond. Basically, the atom's desire for electrons. This desire really represents the attraction of shared electrons to the positively charged nucleus in the atom. So the trend for electronegativity follows effective nuclear charge and is exactly opposite the trend in atomic size. Electronegativity increases from left to right across a row because the effective nuclear charge increases from left to right. And electronegativity decreases down a column because the effective nuclear charge decreases down a column. This table shows values for electronegativity to just 2 sig figs, making it appear as though certain elements share the same electronegativity with other elements. But this is not the case. The only way two atoms can have the same electronegativity is if they are the same element. One rule for determining the skeletal structure of a molecule states that more electronegative elements are usually terminal. Therefore, the least electronegative element in a molecule should be the central atom. This makes sense as highly electronegative elements will want to hold onto their electrons more and are less willing to share with another atom. So they want to form as few bonds as possible and share as few electrons as possible, whereas less electronegative elements will not win in the struggle for sharing electrons and must just be content to share as many electrons as they can. For the molecules below, this method works well for determining carbon as the central atom in CF4 and CO2, since it has a lower electronegativity than fluorine and oxygen. However, for NH3, even though nitrogen is more electronegative than hydrogen, nitrogen has to be the central atom because hydrogen is always terminal. So, while this method fails when there are hydrogens in the molecule, you can still use electronegativity to accurately predict the central atom in Lewis structures. Also, you do not need to know the exact value for the electronegativity to use this rule. Just knowing the general trend for electronegativity in the periodic table is usually enough to determine which element is least electronegative and therefore the central atom. Electronegativity is also useful in determining whether one resonance structure is better than the rest. For this, we also need to introduce formal charge. Formal charge represents the charge an atom would have if all bonding pairs were shared equally between bonded atoms. So for one bonding pair, one electron would go to each atom in the bond. However, this is a fictitious value, as electrons will actually be shared unequally between atoms due to differences in electronegativity that cause the electrons to be pulled more towards one atom than the other. But this fictitious value still has some merit, as it allows us to predict the correct Lewis structure, after considering a few rules, of course. First, formal charge is calculated by taking the number of valence electrons that the neutral atom brings to the Lewis structure, and then subtracting the number of non-bonding electrons and half the number of bonding electrons. Non-bonding electrons are the lone pair electrons, so every lone pair on the atom subtracts 2 electrons. For each bond on the atom, we subtract just 1 electron. First, I challenge you to pause the lecture to see if you can come up with all the resonance structures for the cyanate ion, OCN-, below. I'll give you a hint. There are 3 total resonance structures. Ready to review? This polyatomic ion can contain either 2 double bonds or a single bond and a triple bond, with the position of the triple bond on either the right or the left. To calculate the formal charge for each atom in the structure, start by noting the valence electrons for each atom based on their positions in the periodic table. This is the same for all 3 structures. Then, for the first structure, A, we subtract the lone pair electrons on each atom. So -6 for oxygen, 0 for carbon, and -2 for nitrogen. Then we subtract half the bonding electrons on each atom. So just 1 electron per bond for each atom. This gives -1 for oxygen, -4 for carbon, and -3 for nitrogen. Altogether, this gives the formal charge for each atom as -1 for oxygen, 0 for carbon, and 0 for nitrogen. Note that if you add up all the formal charges on each atom, it equals the overall charge on the structure, in this case, -1. This will always be the case and is a good way to double check your formal charges. Next, we do the same thing for the other two structures. The double bonds in the next structure change the numbers on oxygen and nitrogen significantly, with -4 non-bonding electrons for both and -2 bonding electrons for both. This gives final formal charges of 0 for oxygen, 0 for carbon, and -1 for nitrogen. Note again that the total charge still equals -1, but that the -1 formal charge has switched from the oxygen's position to the nitrogen in this structure. Finally, the last structure has similar values to the first, except they are switched for nitrogen and oxygen, since the triple and single bond have switched places. So, by the end, we have formal charges of +1 for oxygen, 0 for carbon, and -2 for nitrogen, and again, the total adds up to the overall charge on the ion, -1. Since the formal charges are different for oxygen and nitrogen depending on the structure, this is the first indication that one of these structures will be more stable than the rest. If the formal charges are the same for the same elements across all structures, then no single structure is more stable, and all resonance structures are valid. I encourage you to go back to the first molecule in this lecture, the carbonate ion, and prove to yourself that no single resonance structure for that ion is more stable than the rest. As previously noted, always double check that the formal charges on each atom add up to the overall charge on the molecule. For a neutral molecule, they should add up to 0, and for a polyatomic ion, they should add up to the charge on the ion. All three below meet this criteria, so we're good. Next, eliminate structures with high positive or negative values, or those that have fewer atoms with a formal charge of 0. This eliminates structure C. Finally, elements with 0 formal charge are always stable, but negative formal charges are only stable on elements with higher electronegativity, and positive formal charges are only stable on elements with lower electronegativity. Consider the desire of the atom for electrons. A highly electronegative element will strongly desire electrons and pull shared electrons towards itself more, leading to a buildup of negative charge, and therefore a negative formal charge is stable. This rule gives structure A as the most stable structure, since the -1 formal charge would make more sense on a highly electronegative oxygen as opposed to nitrogen, which has a lower electronegativity. Finally, there are some exceptions to the octet rule for certain types of Lewis structures. Odd electron species that contain an odd number of valence electrons can occur, but are rare, so I won't test on these. But you might see some in the homework. These types of molecules are called radicals and are very unstable and reactive. If you study atmospheric chemistry in the future, you will learn about free radical chemistry, as several reactions that occur in the upper atmosphere involve free radicals. Next, incomplete octets, also known as electron deficient or hypovalent molecules. These occur when the central atom lacks a complete octet, and the most notable cases are with boron. This one I expect you to know, as boron is the only element in the second row of the periodic table that does not obey the octet rule. We can also have expanded octets, also known as electron-rich or hypervalent molecules, which occur when the central atom has more than 8 electrons. This can occur with elements in the third row and beyond, so you should never draw a molecule with more than 8 electrons around the central atom if the atom comes from the second row of the periodic table. In the next chapter, we will see many structures that form more than 4 bonds to the central atom, which require an expanded octet, like PCl5 shown below. And expanded octets are also a way for certain structures to minimize formal charges, yielding a more stable structure, as we see here with sulfuric acid. Finally, some general tips. Bottom line, practice drawing structures as much as you can, with as many different molecules as you can find, as repetition of applying the rules and experiencing exceptions is the best way to get comfortable with this approach to determining molecular structure. In the next chapter, determining Lewis structures will be the first step for the next concept we will learn, so we'll get even more practice with this as we move forward. This concludes the third mini lecture for Chapter 6. Please note any questions and ask them on Piazza.